Hello everyone, welcome to the lecture series of KEC 053 with the subject name VLSI Technology as per AKTU syllabus scheme. I, Rajni Prashar, Assistant Professor of Ajay Kumar and Garg Engineering College, is conducting the video lectures on this VLSI technology. Now today we are going to start the 4th unit. It is dedicated to the lithography process, photolithography process. So this lecture is we are going to dedicate for the to the introduction to the lithography. Okay, so sorry, this is the 3rd unit. So under this lithography technique, we are going to study the optical lithography technique. Okay, electron beam lithography technique, photo mask that are used for the lithography technique, wet chemical etching. What is the need of wet chemical etching? Then dielectric and polysilicon film deposition process of polysilicon we are going to study, and silicon dioxide and silicon nitrate process we are going to study in the upcoming few lectures. So what basically is a photolithography process? Photolithography process means we have to draw some circuit over the silicon substrate. Okay, for that we need some specific area, over that area only we need to draw our circuit, right? In the previous lectures, we have seen that we have this silicon substrate, right? We have this silicon substrate and we have grown the silicon dioxide, right? We have grown the silicon dioxide, and when we form the MOSFET, we have this p-type substrate and N plus doping will be done so that we can have the source and drain regions, right? So these source and drain regions are pre-decided that under this area we need to have the diffusion, right? So rest of the area should be protected, right? Rest of the area should be protected. So this protection and the drawn of these areas is done with the help of photolithography process. So we have seen here that we have, let us start from this side. Okay, we have the semiconductor layer, photoresist, some photoresist will be applied, and then mask will be applied, and then some UV light will be passed through this. So as a result, we are going, rest of the photoresist will be removed, and we have drawn this part only, right? So this way we are going to develop the circuits. So it is known as photolithography process. Okay, so introduction to photolithography process. The lithography is a Greek word which means printing pattern on the stone. Okay, so it is like the printing some circuit on the wafer, right? So in IC fabrication process, photolithography, light silicon wafer printing is done. In semiconductor industry, the doping of impurity is done in the selective area. We have seen in the previous slide, right? We know that the doping should be done in the dedicated areas only. So these regions where the dopants have to be incorporated is selected and marked by the process called lithography. Lithography is something referred to, it is also referred to as photolithography. Okay, the lithography or the photolithography is a process of transferring the pattern from a mask to the silicon wafer. So first of all, we start with the coating the silicon with the radiation sensitive polymer film that is known as photoresist. So the very first step is we have this silicon substrate. Okay, we have the silicon substrate and we have the oxide layer, right? We have the oxide layer. Over this oxide layer, we are going to apply the photoresist material. Okay, we are going to apply the photoresist material. If we need to draw something, if we need to stick something over another thing, we need to have some sticking material. That sticking material here is your PR, photoresist material. Okay, when the resist is exposed to a particular type of radiation, the properties of this PR material will be changed. Okay, so depending upon the PR material which we are going to have for each photolithography process, we are going to have the different PR material, and the different types of radiations will be used for each material. Okay, so depending upon that radiation, the properties of PR material will be changed, and some portion will be remain there, and rest of the portion will be removed. So take 1 or 2 drops of this viscous liquid, that is PR material, put it on the silicon wafer, and then quickly spin the wafer at 4000 rpm approximately, so that a very thin uniform coating of this resist film is deposited over the wafer. So what we are going to have? We have this some turnable table, we have the substrate over that. We are going to apply the PR material. A few drops of PR material will be passed. It is rotated so that this PR will be spread uniformly over the substrate. Okay, so we have seen after drying, after rotation, when it is applied over the substrate, it is dried, and then the process is repeated for the further processes. Okay, the resist thickness is given by the formula T is equal to under root Kp divided by W1, where K is the spinner constant. It lies between 80 to 100. P is the resist solid content in it is in the percentage, and W is the spinner rotational speed in RPM per 1000. Okay. Second step is to expose this resist wafer to proper radiation, and that is to the radiation to which the resist film is sensitive. Okay. Then the optical plate is nothing but a glass plate which with this transparent or the opaque regions. Okay, so we are going to have some mask over there. For example, okay, I am taking the same example again and again so that you have a better understanding of the same device. We have this P-type substrate. Okay, then over this PR will be applied. We have this SiO2, PR will be applied, right? And over this we are going to apply the mask. Right, it will have something like this. Okay, so then UV light will be passed. We are going to pass the UV light. Okay, then UV light will be passed. Then some portion it will be some portion will be hardened and some portion will be softened, right? So under this we are going to under this PR material will be soft, so it will be removed during the etching, and rest over it will remain there. Okay, so we are going to remove PR and silicon dioxide over these areas, and after that we have the dedicated area where you don't have the silicon dioxide, and over that area we are going to diffuse the N+ doping. So when the photoresist coated wafer is exposed to UV light, the exposed resist has properties changed, and suppose the exposed portion have become soft and it can be easily removed. This wafer is now soaked in a developer solution, and the process is called the developing. Okay, so let us see the diagram quickly. We have the substrate, we have the PR, it is exposed, and then after exposure some portion will be soft and some portion will be hard. So we can see that it can develop in two parts. So in this part here your section will be soft and it is removed during the etching. Here it is hard and it remains there, and we have the doping over this area. Okay, so this way we are going to develop the circuits. So when we put it in a developer solution, these portions go away and leaving behind with the resist film only in the unexposed regions. We have transferred the pattern from the mask onto the resist on the top of the silicon wafer. Now in most of the case, this wafer will have the oxide layer on the top of the surface, right? On the top of the surface, which we coated the resist, and it is generally oxidized surface. So photoresist is protecting certain regions of the, it is protecting certain region of oxide, and certain other regions from where the resist is removed is now exposed to the external environment. So when we put it in a dilute hydrofluoric solution, these portions of oxide will be get etched, and the process is called the etching. Okay, the purpose of the photoresist is achieved. Now we can remove this photoresist material, and now windows have been created over the wafer where the doping will be done as shown in the previous diagrams, right? The pattern of the mask and the pattern on the semiconductor, if the pattern of the mask and the pattern of the semiconductor is identical, it is known as positive photoresist, where the exposed resist gets softened. Okay, where your resist is exposed to UV light, it gets softened and it is removed during the time of etching. It is known as positive photoresist. So we could have the another type of photoresist also. The resist could have got hard in the regions where it is exposed to the radiation, fine. So hence it is known as negative photoresist. It is known as negative photoresist material. So positive photoresist material is one which gets softened when it is exposed to the radiation, and the negative photoresist is one which gets hardened when it is exposed to the radiation. So we have seen two type of photoresist material. Depending upon the application, we can select that any one among them. So before starting the photolithography process or any process, we need to clean the surface. Okay, the typical contamination that must be removed prior to any process, prior to photoresist coating process. It can be dust from the scrubbing or cleaning. It is minimized by the laser scrubbing. Then photoresist residues from the previous photolithography process, it can be minimized by performing the oxygen plasma etching. Then atmospheric dust, it can be removed by having the good ambient, good clean room, and the bacterial contamination can be removed by good DI water, deionized water. It is known as deionized water. Okay, wash the wafer with deionized water and your bacterial contamination will be removed. Okay, so here we have already seen this slide, the coating of photoresist material. So this coating of photoresist material, it can be done, it can be spray coating. Okay, resist is sprayed onto the substrate. Dip coating, substrate is dipped into the resist and lattice flow with the gravity. Meniscus coating, the substrate is inverted and pull over the resist bath. Plasma coating, a thin photoresist film can be developed by certain plasmas. Okay, so we can have the different coating techniques also. So right, when we suppose we have liquid over there, if you remove this surface very quickly at a very high RPM, it will be spread all over the surface uniformly. So this graph shows that if you increase the RPM, your resist thickness will be decreased, right? So we can see that your resist thickness for different type of resist material, we have these different type of resist materials, right? We have SPR 222, right? 7.0, 4.5, 3.0, 1.5 and 1.2. They are the different resist, they are the names of the different resist material which are used in the semiconductor industry. Okay, so if you increase the RPM, we can see that their thickness is reduced, right? So for each graph we can see that the thickness of the resist is reduced. So the main performance parameter for the lithography process, there are main two parameters which should be kept in mind while performing the lithography. The first is the figure of merit. In figure of merit in lithography process, some figure of merits. The first one is the resolution and the second one is the throughput. The resolution obviously means the minimum feature size that can be achieved with the help of one particular mask, right? One particular lithography process. That how identical the circuit is as compared to your mask, right? So how good is the resolution? That is how close the mask, how close to the mask it is. So the resolution doesn't only mean the minimum feature size, it also means the precision with which the minimum feature size can be incorporated over the silicon substrate, right? So second important feature is the throughput. Throughput is that how many wafers we can process with one mask. Okay, so with one mask, how many wafers we can process with one mask in a given time. And we also have one third figure of merit, that is the depth of the focus. Okay, so let us quickly discuss the type of the lithography process. We are depending upon the light which we are going to use, depending upon that we can classify the lithography technique as optical lithography, e-beam lithography and X-ray lithography. In case of optical lithography, the resist used is known as photoresist, which is sensitive to the light and the light can be UV light. Okay. In case of e-beam lithography, the resist is called e-beam resist and that e-beam is sensitive to electron beam only. And e-beam lithography can also be done without mask. The direct writing can be done where we have to write, where we have to draw the circuit, beam will be there, else we are going to switch off the beam. Okay. So e-beam is one process where we can directly write on the directly writing is possible with the help of this e-beam pen. Next we are going to have the X-ray lithography. It is optical lithography, only instead of UV light, it is an example of optical lithography, only instead of UV light we are going to use the X-rays. Okay. So the basic steps which we are going to follow in any lithography process. So first we are going to discuss the optical lithography. Optical lithography is a photographic process by which the light sensitive polymer called photoresist is exposed, developed to form the 3D image on the surface. In general, the ideal photoresist image has the exact shape of the design or intended pattern in the plane of the substrate with the vertical walls through the thickness of the resist. And the general sequence, this is the general sequence which is carried out in any photolithography process. First one is the substrate preparation. We have to prepare the substrate, we have to clean the substrate, previous contamination should be removed. Then photoresist spin coating is done, pre-bake is done to dry this spin, to dry this photoresist material. It is exposed to the UV light, then post exposure, bake and development, then post bake. So let us show the let us check the diagram quickly. We have this wafer, over this PR is applied. This PR is a liquid material, so it should be dried. It is pre-baked, then aligned mask is used, right? We can see that we have the mask, then it is passed to the UV light. Under development solution, this will be where it is not exposed, it is not exposed to the UV light, that will remain hard and rest will remain soft. So during the etching, during the development, we are going to have this kind of structure, and during etching we can see that some portion is removed over this, the oxide under this will be removed, and we are going to strip the PR. The function of PR is done, so we can remove the PR in the last step. So first processing step is the substrate preparation. Substrate preparation is intended to improve the adhesion of the photoresist material to the substrate. Like suppose we have one substrate, over that we have to apply the PR material, photoresist material. If that substrate has the contamination or dust particle over that, your PR will not be will not get stick to that properly, right? So it is done to improve the adhesion to the substrate. It is accomplished by one or more following process, that is substrate cleaning to remove the contamination, baking to remove the water molecules, if it has some water molecules over that, it should be removed. Addition to that, addition promoters to keep the water from coming back. Then substrate contamination can take the form of particulates or a film that can either be organic or inorganic. Particulates results in defects in the final resist pattern, whereas the film contamination can cause the poor adhesion and subsequently loss of the line of its control will be there. So if your PR is not properly stick, when we pass the UV light, it will not be properly aligned and some misalignment of circuit will be there. So one type of contaminate absorbed water is removed most readily by high temperature process, that is called dehydration bake. Dehydration bake, as the name implies, removal of water from the substrate by baking it at a temperature of 200 to 400 degrees C. We bake the wafer at 200 to 400 degrees C for about 30 minutes to 60 minutes, so that if it has some water molecules, it will be removed. The substrate is then allowed to cool, preferably in a dry environment, and then the coated as soon as possible. The coating of PR is done as soon as possible. The typical dehydration bake, however, does not completely remove the water from the surface and of silica substrate, which includes the silicon, polysilicon, silicon dioxide and silicon nitrate. They can also be formed with the help of these lithography process. Next, this surface silicon atom bond strongly with the monolayer of water molecules and it will form the silane group. So that will be removed, that should be removed. The preferred method of removing this silanol group is by chemical method. The addition promoters are used to react chemically with the surface silanol and replace the OH group with the organic functional group, and unlike the hydroxyl group offers a good adhesion photoresist. So the silane are removed and over that your organics will be added, and for this purpose mainly we use the HMDS, that is your hexamethyl diselenise is the most commonly used material in this process. Next processing step is the photoresist spin or coating. A very thin uniform coating of photoresist at a specific well controlled thickness is accomplished by the process of spin coating. The photoresist is in the form of liquid. So liquid, if it is not in the form of liquid, that is converted into liquid and it is poured over the wafer, and then it is spun at a very high speed to have a very uniform layer throughout the wafer. To achieve the desired thickness and uniformity, there is a choice between the static dispense. Static dispense means when your wafer is stationary and we are spreading the resist all over the wafer. And in case of dynamics dispense, your wafer will be spinning. And your the tap from where the photoresist material is coming, that should be stationary. Okay. The spin speed, time, accelerations to each of the spin speed matters for the uniformity of the substrate, and also the volume of the resist dispensed, the property of the resist materials such as viscosity, solvent, their composition, they always play a very important role as a property of photoresist material. So here we can see we have the spin time, okay, the spread time and then the spin time. Spin time is more as compared to a spread time, and here we can see the photoresist thickness. If you have a very high viscosity, it will be decreased gradually, okay, and we have the low viscosity material, it will also be decreased gradually if you increase the spin speed. The photoresist spin speed curve is essential tool for the setting the spin speed to obtain the desired photoresist thickness. The final photoresist thickness varies inversely with the square root of the spin speed and is roughly proportional to the liquid photoresist viscosity, right? So this is all about the, we have just covered the two steps. We have just started the optical photolithography and we have just covered the two steps. Rest of the steps will be covered in the next lecture. So we have seen in the today's class that what basically is photolithography, what is the need of photolithography and what are the types of photolithography. Two types of photoresist materials we can use, that is positive photoresist material and negative photoresist material, right? And we have started the optical photolithography where we use UV light as a source material, as a UV light, and the photoresist material as a PR, photoresist material. Okay, so rest of the process will start in the next class. Thank you so much.